Hey folks, this is Tom Crawford and welcome to the third video in our opacity series. Now this video is going to be fairly short, but it's going to focus mainly on ISO opacity. Okay, so up to now, our first video, we talked about kind of the history behind opacity and the things that really affect opacity. And we're going to come back to that in video 4 as we kind of wrap things up. The second video, which hopefully you've watched, we talked about tappy opacity and what makes that up. This video, we're going to talk about ISO opacity. Okay, now ISO opacity is kind of formed out of what was originally done in the tappy method. Okay, so some things that they like there that they wanted to take advantage of, but also some things they wanted to change. And we're going to focus here really on how the measurement is set up. Okay, so much like the tappy method, they wanted to create a contrast between two items, with a single sheet of paper backed by something that's radically different than the other. Okay, so what they chose to do is to use a black cup. Okay, so we have a black cavity, and what you do is you back a single sheet of paper and you back it by the black cup, so that if any light is transmitting through that paper, which odds are it's going to, that light's going to be absorbed by this black cup. Okay, and it's not going to come back out again. You're then going to take that and you're going to back that single sheet of paper by an infinite pad of similar material. Okay, the thought being is that how do you view most paper? You view most paper in a book form, a magazine form, a newspaper, whatever it might be, and so its backing should match or mimic whatever it's made of, right? So the ISO method uses what's called an infinite pad backing. Okay, and an infinite pad is that, all right, if this is my measured sample, single ply, the infinite pad is a sufficient number of materials that whether I put a white tile back here or a black cup back here, it doesn't change the reading. Okay, so on copy grade paper, that's typically 5 or 6 sheets of paper. We'll do something like that. If you take tissue, it could be as many as 20 or 30. And as the heavier the grade gets moving towards board, it may be a single ply is all you need, but you want to make sure that the backing does not affect the reading. So they came up with a method, a calculation for opacity that was called R0 for the measurement of a single sheet of paper backed by the black cup, and you divided that by R infinity, which is the infinite pad. Okay, so it's using a single sheet of paper backed by an infinite pad of material. Okay, so that became the calculation that's used for measuring the opacity according to the ISO method. All right, now, so that's the calculation. Let's look at the geometry used to measure ISO opacity. Now, if you watch the tappy video, you've seen this guy before. So what the ISO community wanted to do, and this is again in the 1950s when they're developing this method, and they had just completed the method for doing the ISO brightness, and they said, you know what, we like this geometry, this sphere, and it would be handy if our customers could use the same measurement technology for both brightness and opacity, and so they looked at how they could use this to make that measurement. And so with this, what you have is you've got a sphere, and that sphere is coated with a very high reflectant matte white coating. Okay, so the goal being is that if this is my light source that sits here, light shines into the sphere, light bounces off the sphere walls, and the goal is as that light illuminates the sample which sits here, as the energy strikes that sample, it's going to be equal from all angles. Okay, so it's going to have a diffuse illumination. All right, so this method, the ISO method, has what we call a diffuse illumination because light's striking the sample from all angles. Okay, now in this method, the photocell sits here, which is directly above the sample opening, okay, where the sample is going to sit. Now, just as a reminder, when we talk about instrument geometries, right, if this is my sample, the instrument geometry is perpendicular to that, so it starts there. So the perpendicular axis represents 0 degrees. Okay, so in that case, if the sample is sitting here on the surface, 0 degrees is directly above it. So in the ISO method, we have a diffuse illumination 0 degree viewing. Okay, so if we draw that out, so let's say this is our sphere. The sample sets down here. You've got a light source over here which is illuminating the sphere, right? And your photocell sets right here. So it's directly looking at that sample right there. Okay, so diffuse illumination, 0 degree viewing. And that became the method, which was very nice because if I had an ISO brightness, I had the geometry that I needed to make the ISO opacity measurement. Major difference though is where do you make the measurement? Where brightness is a measurement in the blue region of the spectrum, opacity is typically measured, not typically, opacity is measured out in the center of the spectrum. The ISO community looked at different defined color areas and decided that they wanted to use something in the center portion of the spectrum because our eyes respond to light best out there in that center region of the spectrum. And they said, okay, where would it make sense to make a measurement? They looked at defined and known areas that they could use, and they decided on what's called a luminance C and the Y function. Now, luminance C is a colorimetric definition, which we will get into when we talk about color in a few videos from now. And the Y function represents the center portion of that, which is the green region of the spectrum, with the primary wavelength, the dominant wavelength, being 557 nanometers. So, measuring light, it's a broadband filter, much like the TAPI method is here. It's looking at a fairly large region, but with most energy in the center of the portion of the spectrum, and that measures at 557 nanometers. Okay, so we have a geometry, which is diffuse illumination, 0 degree viewing. We have a spectral region, which is here in the 557 nanometers. We've defined the calculation that we use for opacity, which is R0 divided by R infinity. Okay, and so that makes up ISO opacity. So if you've watched the TAPI method, you know that this defines what we do in the TAPI world. Now we look at this and I say, okay, this is the ISO world. And the two can be quite different from one another. And so what we're going to do in the next video is we're going to talk about some of those differences a little bit further, define that a little bit more, and then we're going to wrap that up with talking about whether you're using the ISO method or the TAPI method, how these things affect opacity. All right? Thanks for watching.